Thank you for that introduction, Emma. Yesterday I mentioned that I was so nervous if I'd been holding a tambourine you wouldn't have heard anything. Thankfully today my Nuffield senses have kicked in and it's almost time for a beer. So I am Wade Mann. I'm a proud 2015 Nuffield Scholar and my subject is on integrated pest management strategies for greenhouse hydroponic berry crops. And today I hope to show you or give you an alternative perspective. My wife Nikki is also a Nuffield Scholar from 2014 and together we run an operation on the central coast of New South Wales. First and foremost, I'd like to express my deepest gratitude to Nuffield Australia, who have stood by their decision to support my scholarship program despite a record number of successful horticultural applicants in our intake. I think there were 9 of us all up. I'm truly humbled by your investment in me. So berries by nature are an easy pick and ready to eat fruit without the necessity for peeling. And as a result, we need to be aware of the food safety, the maximum permissible residue levels, and also the limited number of chemical controls that are available to pest and disease control. So these factors are the underlying motivation for primary producers in the berry category to adopt IPM strategies. So my primary objective was to look for emerging and innovative technologies in integrated pest management globally. And armed with the Nuffield Golden Key, my plan of attack was to approach a number of research centres and universities through the majority of Europe, the UK, the east and west coast of the USA, Canada, Hawaii and New Zealand. I also met with a lot of breeders of biological products, that's both biocontrol agents, from a physical point of view as well as from the actual chemical point of view. I also went to a lot of plant breeders to try and see what their breeding programs included in terms of resistance management. And finally, I also got to see a cross-section of growers. I got to see small-scale growers. I got to see large-scale multinational corporations. I got to see entry-level type structures. I got to see the real sophisticated glasshouse type structures, and it gave me a good idea and a good perspective of how IPM should be adopted in each one of these sectors. So integrated pest management is basically a combination of physical, cultural, biological, and at the end of the day, chemical controls. It's a combination, it is not one or the other. But ultimately, we are looking at the first 3, the physical, the cultural, and the biological, as an early approach, and the chemical side of it as a last resort. So the primary focus of physical controls relates to the enhancement of the optimum growing environment and the protection of the crops from the various climate as well as pest and disease elements. And I guess the main limitations, if we look at those tools up on the left-hand side there, the main limitations and variations in the levels of controls implemented are based on the level of investment and the obvious cost-benefit outcome. You can see there sophisticated glass houses as well as I mentioned earlier on, entry-level type tunnel structures in Spain. We also have natural physical controls, and these have been used quite extensively more recently, and they have benefits of non-commercial type crops, providing a range of options in managing and implementing biological pest control. So for example, on the top right-hand side there, you can see a potted cereal plant. It's actually barley, and that barley is infected with what we call a cereal aphid. The cereal aphid has absolutely no impact on strawberries, raspberries, blueberries, for example. It's specific to cereal type crops. So they're infected with that aphid. We then apply a parasitic wasp which uses that type of aphid as its initial food source, and then it moves on into the crop. We also have sorry, I've lost my words here a little bit. We also have indicator and trap plants which allow for early detection of pest incursions. We have companion plants which generally attract pollinators but also provide pollen for some of our biocontrol agents, which if their food source is at a low threshold, they're able to use that pollen as a supplement to sustain their breeding cycles. And lastly, we also have nature strips which are generally planted outside of the greenhouse environment, and these attract and repel some of the beneficials and some of the insect pests. So in terms of cultural controls, we're trying to alter the environment or the condition of the host or the behavior of the pest and disease to prevent or suppress any incursions. And again, what we're looking at here is trying to provide an environment that is clean, and in terms of sanitation and hygiene and biosecurity, we're trying to make sure that we have good plant material establishment. We're looking at nutrition, we're looking at correct water management, and all of those separate tools are used to try and ensure that we have a clean environment to start off with. And you'll see there's a couple of funny looking fellas on the bottom left-hand side there wearing funny suits and boot covers and so on. We didn't have to wear hair covers because I was the only bloke with hair at that time. But ultimately, it's all about maintaining biosecurity and making sure we don't contaminate that enclosed environment. So with regard to biological controls, we have three main types. These are predators, and these predators come in many forms: predatory mites, predatory bugs, predatory lacewings, predatory beetles, and even predatory thrips. We have parasitoids, which are tiny little parasitic wasps. They don't sting you, they don't hurt you. In fact, they're very small and hard to detect. And more recently, we have these parasitic nematodes that we're able to apply as well. They come in various forms. So if you look at that top middle picture, you can see a sachet on the left-hand side, and you can see some bottles. Because these little biocontrols, for example, predators, are so small, we have to use a carrier material to help us to disperse them throughout the greenhouse. If you look at that top right-hand slide, you will see there are 500,000 of what we call predatory mites within that bottle. Those 500,000 predatory mites would service an area of about 10 hectares. But you've got to be able to shake them out because they would all fit on basically 1 tablespoon. So if you suffer from something like regular sneezing, you'd probably disperse them in one flat smack. So the 4 key sort of pests, as far as I'm concerned, both in Australia and from a global context, are aphids, thrips, whitefly, and two-spotted mite. And there are many, many variations of these. But basically, all of these 4 main insect pests are what we call piercing and sucking pests, and they are very taxing to the plant. But just in reference to aphids, thrips, and whitefly, these little fellows also have the ability to vector and transmit diseases such as tomato spotted wilt virus, which can cause some incredible economic damage to crops. I'm not going to run through each individual type of beneficial there. I'm just going to pull out a couple which I think are most interesting. And so I'll draw your attention to the bottom left section there, which is Aureus amatus, and which is found in Australia. It's a native predatory bug, and it has the ability to predate on every single stage in the life cycle of a thrip. So it will eat the egg, it will eat the juvenile stage, it will eat the pupal stage, and it will also eat the adult. Whereas some of the other biocontrols will only target one of those stages. So this is a great invention in Australia, and it has only recently been released. You can see the container on the bottom left is holding what we call buckwheat. Buckwheat is the carrier material. It also has some pollen in it to help establish the numbers of that predatory bug. And ultimately, you can see on the right-hand side, bottom right-hand side, a strawberry flower with the adult Aureus amatus on there, looking for thrips. In terms of aphids, we basically are limited to what we would call parasitic wasps. And if you look at the top right-hand picture there, you can see an adult parasitic wasp stinging an aphid. It injects the aphid it injects an egg into the aphid. That egg hatches as a little larval form, and it eats the inside of the aphid out, and that's how we control aphids. That bottom picture in the middle there is some parasitized aphids in our raspberry crop on our home project. Whitefly also are generally controlled by parasitic wasps, and perhaps one of the latest releases, which is actually a biological supply company in Loxton, South Australia, is this little fellow called Nufฟี่tenuis. This is a predatory bug as well, and it also has the ability to control each of the stages of the life cycle. It is only at the moment being used in tomato glasshouse production, but I think it has immense possibility in the greenhouse berry side as well. Two-spotted mites are probably the biggest problem worldwide, not only in berry crops, but also in a lot of floral crops and so on. And the 2 main predatory mites to control two-spotted mite are Nufฟี่californicus, which is generally used in very hot, dry climates, and then Phytocilus persimilis, which is used in the other sort of temperate stroke high humidity type climates. Phytocilus persimilis is a bit of a problem because it has to be reared on plants itself, and that becomes expensive. And then they have to wash those mites off the plants and then put them into these containers to be dispersed in the crop. So in terms of natural biological chemicals, we have 2 main types. We have those which are targeting plant diseases, and then we have those that are targeting the insect side, the pest insect side. And if I just quickly read through the top 2 sections there, we've got hormones, we've got growth regulators, we've got enzymes, we've got all sorts of vitamins for the plant side of things. And then on the insect side, we've got also pheromones as well as semiochemicals and growth regulators. But I would really like to draw your attention to that bottom section. And these are basically fungi and bacteria that are naturally occurring within the soils, within the environment. And they have been cultured to control either the plant side of things or the pest side of things. And in terms of The plant side, basically what we're looking at is using some of those spores to colonize either the root system or the surface of the leaf where we have disease taking place. And a number of those spores will then colonize those diseases, and in the same manner they will also colonize, for example, around insects. So if I look at Bouveria bassiana, for example, in this slide, you can see a slight deformity in that immature strawberry on the top left, and then you can see the mature strawberry, which is really looking a little bit gnarled. As a result of, you can see top right hand side, a nymph of the lygus bug, and then you can see a little bit further down on the right hand side the adult lygus bug. It's then been sprayed with this Bouveria bassiana, and you can see how those spores have colonized and basically rendered the adult ineffective. If we'd used chemicals, you probably would have seen something similar to the bottom right hand side. The insect would be dead, but you would see no spores all over it. So this is a technology called entomovectoring. It was really a concept that I was most interested in. Unfortunately for Australians, we're prohibited from using bumblebees commercially, but in the European areas as well as Canada and America, they are using bumblebees quite effectively to pollinate their crops. And what they've figured out is that they can actually use the bumblebees if they retrofit what we call an inoculum dispenser to the hive. The bumblebees, as they move out of the hive, will walk through a powder which we call a vectorite. That powder, as you can see on the bottom left-hand corner there, sticks to the hair on the legs and the underside of the bumblebee. And as it flies on its merry way to pollinate crops such as berry crops, they deposit this microbial formulation, which could be an entomopathogenic fungi or just a plant disease attacking fungi. And as it deposits it on there, we basically have control. So it's a major labor-saving exercise, and we don't have to wet the crop. So as I say, the issue in Australia is that we only really have the European honeybee and certain other native bees available. And at the moment, these are very difficult to harness because, for example, the honeybee has a very sophisticated social structure. And so when it sends its little scouts out, they don't just go to the raspberry plantation or the blueberry plantation because they don't want what we call monodiversity. They want multi-floral diversity. They want to make sure that they have different forms of protein from the pollen. So stay tuned. I think that is a technology we need to be watching for. So lastly, in those controls is chemical controls, and I only really want to tell you that you need to be aware of the mode of action. We need to know what we're trying to target, where we're trying to kill the pest. So is it in the nervous system, is it in the reproductive system, or is it in the feeding system, for example? And we need to make sure that we rotate the chemical groups. If we use the same chemical group over and over, we get resistance, and then we really do have dramas. So ultimately, we need to use these as the very, very last resort, and we need to be aware of the fact that we need to look at the least toxic formulation possible so that we don't impact on those beneficials that have already established in the crops. So some of my unexpected observations, without getting too technical, trichomes are just like the little hairy parts, little thorn parts on the underside of, for example, a raspberry leaf. And what that lady there on the top left-hand side is trying to show me is that there are certain beneficials, which are predatory mites for the most part, that don't like these trichomes. So there's no point releasing that beneficial into a raspberry crop if it's not going to climb up that plant. So we need to be aware of which ones are effective or ineffective in that case. In Europe, they use a lot of pollen supplements to try and keep those colonies of beneficials going. So if the food source does become quite low, instead of them dying out or moving on to other crops, they basically supplement the crop with pollen, and that pollen helps to keep them sustained. Auto-dissemination, if you look at that picture on the right-hand side, again, there's a funny-looking bloke with hair there, but that is basically a yellow canister, and the bottom part has got what we call a hormone or a pheromone for insects as an attractant. There's a hole on the top lid part which is screwed onto that base, and that hole basically is where whatever the pest issue is, normally fruit fly, for example, flies into that hole. Within the lid, there's a little bit of gauze wrapped around the inside, and on that gauze is an entomopathogenic fungi that is rubbed onto the gauze. So as the fruit fly flies in, it sits on the gauze and it doesn't realize it's being basically touched by and rubbing that entomopathogenic fungi onto it. And so as it flies away, it starts to become colonized and eventually it dies. Another very interesting point is the reduction in the number of instars, and these are basically the developmental stages in insects. So in protected cropping, because the environment is so good and so conducive for growth, we're starting to see insects growing at one hell of a rate. So this becomes an issue if we have a beneficial that only targets a certain life cycle stage. If there isn't that opportunity, we can't use that beneficial. Spotted-winged Drosophila is not present in Australia yet, or not declared anyway. It's a major issue all over the world other than Australia. But as a result of this problem, what growers have done is they've really improved their hygiene protocols. Lastly, on this slide, gene editing is also an option that people are looking at. So at Rothamsted, they're looking at gene editing in beneficials so that if we have to spray toxic chemicals, we don't kill the beneficials. They become resistant and they obviously continue in their natural forms. So my key learnings are timing. Timing is the most important. We need to look at prophylactic type releases. Early and often is better than late and then you're chasing your tail. Balance is important. We need to understand and respect the fact that we're never going to have 100% clean crops. We're always going to have some pests, but we need to make sure we've also got beneficials. There needs to be more focus on plant disease biocontrol agents. Plant diseases form resistance so much more quicker, and there's so many different isolates and so many different strains. Biologicals need to be competitively priced so that we can release them early and often. If they're very, very expensive, they become a last resort and they don't work. So for example, those sporal formulations that we have, we need to be able to release them 2 to 3 times in a 5 to 10 day period so that we get sufficient spores to colonize some of those pest problems. Controlled release sachets are not available in Australia. They're available in Europe because they're quite an expensive method of releasing beneficials. But essentially what happens in that sachet, we have what we call a type of bran. That bran gives rise to a type of fungi. That fungi is the food source for feeder mites, and the feeder mites are a food source for the predatory mites. So we have this whole ecosystem taking place within that sachet. We then release that sachet into the crop, and those little predatory mites are released in a gradual phase. Here in Australia, we have to release them literally instantly, and we expect them to take control of the crops. This is a slightly better form, I believe. And last but not least, we need to look at more biostimulants. And these are basically having impact on the efficiency of plant metabolism. They help to increase the tolerance to abiotic stresses, which are basically climate stresses. And they also facilitate nutrient translocation, which ultimately enhances plant vigor. I'd like to thank my fellow Japanese ninjas who accompanied me on our GFP trip. They became my extended family, and we formed some strong friendships there. I'd like to thank the 3 Musketeers. I have 2 sons proudly serving in the Royal Australian Navy, and I have my daughter here in her last year at school. She's also a part-time strawberry picker, probably one of the best as well. So in all my travels with Nuffield, I've learnt about biostimulants, biofungicides, biopesticides, biofertilizers, you name it, but nothing beats BioNic. Thank you very much.